I will explain the Parametric Road workflow. All design input values used in this example are based on preset data, not separately prepared manual data. First, select Parametric Road from the workbench. Then create a new document. You can see that a document has been created in the tree window. Open the Project Setup menu to configure the basic settings for road design. In the settings, the design standard can currently be selected based on Korean or US standards. Next, set the coordinate system. In this example, the user can directly modify it to use the UTMK coordinate system. When you click the Apply Setup button, objects are created in the tree window. This is the step for creating the tin terrain. The triangulation data can be edited directly through each tab menu. Terrain data can be imported from a CSV file. You can also create a tin terrain using predefined sample terrain data. After importing the terrain coordinate data, you can confirm that the tin terrain has been created. The generated tin terrain can be viewed using FreeCAD's Fit Selection command in the 3D view. You can see that the tin terrain has been created in the tree window. Next is the step for creating the horizontal alignment. If there is an alignment object created in FreeCAD Sketcher, it can be brought in and used here. Alignment data can be imported from a CSV file. By applying preset alignment data, you can create a road centerline that includes tangents, curves, and transition curves. Horizontal alignment data can be imported so that it matches the position of the tin terrain. Road design standard data can also be configured. Now I will create the alignment data. It has been created, but it is not visible because it is covered by the terrain. If you hide the surface in the tree window, the created alignment becomes visible. Now I will create the stations. You can set the station interval and station symbols. The created station information can be checked in the table and in the tree window. In this step, we will work on the profile. Using preset profile data, the design elevation, profile grades, and vertical curve information are configured. Here, I will simply create a profile using two PVI points, the start station and the end point. I will enter a large elevation difference between the start and end points, then simply interpolate the intermediate values. You can see that the profile object has been created in the tree window. In Profile Review, the created profile plan is reviewed. The relationship between the existing ground elevation and the design elevation is checked, and the profile grades and major change points are reviewed to confirm the intended design flow. This is the step for creating the 3D centerline. The horizontal alignment and profile information are combined to create the 3D centerline. This 3D centerline is the key reference line of the road model and includes both position and elevation information. An assembly is created to define the road cross-section configuration. Basic cross-section elements such as lanes, shoulders, and slopes are configured using preset assembly data. An assembly is not just a simple shape, but a cross-section design rule that can be repeatedly applied to each road segment. Using the Show button or the Fit Selection function, you can check the assembly in the 3D view. The entire road section is divided into regions according to the design conditions. Using preset region data, the road cross-section application structure for each segment can be set up quickly. By linking with the assembly created in the previous step, the cross-section configuration to be applied to each region is specified. In this menu, structure-related elements are configured. Based on preset structure data, the structure information required for the road section is set. It can include various structure types such as drainage structures, bridges, tunnels, and retaining walls. When you click a row in the upper table, the related detailed information can be checked in the lower section. Drainage connection points represent the points where structures and drainage elements are connected. The generated structures can be checked in the 3D view. The structures shown on the screen are drainage structures. They represent the inlet, outlet, culvert, and pipe. These will be enhanced in more detail in the future. This is the step for configuring drainage-related information. Since the drainage preset data was created in the previous step, I will continue here by selecting Drainage Structure Flow. The drainage structures created in the Structures menu are configured with connected drainage flow information. Using the Show Flow Network button, the drainage flow network can be checked in the 3D view. The drainage flows are visible except for the ditch. The flow connections between each drainage element are represented as flow routes. Drainage information is an important design element that is connected to the road surface, cross-section configuration, and future review results. In Drainage Review, the configured drainage conditions are reviewed. The drainage locations, flow directions, and major low-point conditions are checked to confirm that they are properly connected with the road alignment and profile plan. Applied section creates the actual cross-sections applied at each station. When you double-click a created row, you can check the cross-section shape applied at each station in the 3D view. Assembly, region, terrain, structures, and drainage conditions are combined to create the applied section for each location. Based on all the rules, data, and design conditions defined earlier, the parametric road model is built. View options can be adjusted through the tab menu. While the model is being built, the horizontal alignment, profile, 3D centerline, cross-sections, structures, and drainage information are internally connected into a single road model. The generated road model can be checked in the 3D view. By double-clicking an item, only that item can be viewed in the 3D view. This process is not simply drawing individual elements, but creating a traceable structure from design intent to the resulting model. In Review Cross-Sections, the generated cross-sections are reviewed. The cross-section shape at each station, its relationship with the terrain, the applied assembly, and region information are checked. By reviewing each cross-section one by one in the 3D view, you can confirm whether the road design result matches the intended design rules. In the canvas view, the cross-section can be enlarged and examined in detail. The cross-section viewer is not an editing tool, but a review screen for checking and verifying design results. In this step, the earthwork results are reviewed. Based on the difference between the design cross-section and the existing terrain, the cut and fill conditions are checked. In the Build Parametric step, I will change the View option so that the entire surface can be viewed. Although this example is based on preset data, the earthwork evaluation flow can be checked in the same way as in an actual road design review. Finally, I will summarize the tools that will be expanded in the future. Deliverable output features are planned to be added in the future. Structure output will also be enhanced in the future. AI Assist will also be expanded later with features specialized for road design work. The watertight solid modeling function will also be further enhanced. Currently, some structures are represented with simple shapes, but in the future, detailed modeling required for actual structure design will be improved and supported. Now I will output some structures as solid models. When the surface model is hidden, the solid models of the structures become visible. This concludes the overview of the main features and workflow of Parametric Road.